Hi all, let's take a look at the Achieve 4.5 homework assignment covering L'Hopital's rules. This time, I think instead of going back and forth between the actual Achieve assignment page and my work, I think I'm just going to keep my work maximized for the very reason that the problems on Achieve I was able to write out, and the only answers are the numerical answers through here. With the exception of the first three problems. The first three problems all ask us whether or not L'Hopital's rule should even be applied. And that's a very easy question to ask. Remember, L'Hopital's rule only applies to indeterminate limits. What's an indeterminate limit? Well, an indeterminate limit, when it's in fractional form, has to either be 0 over 0 or infinity over infinity. If it's not one of those, then it's not something that L'Hopital can handle. In fact, if you try to use L'Hopital on it, it's going to give you a wrong answer. So in this first one, it was just asking, does L'Hopital's rule apply? And all I had to do is quickly plug 20 into that denominator and say, well, the denominator is not 0. Therefore, since it's not 0, L'Hopital's rule does not apply. In the second one, same thing. If it's not 0 over 0 or infinity over infinity, L'Hopital's rule does not apply. If you try to plug a 3 into your denominator, you would get an 18. As soon as you know that, you know L'Hopital's rule does not apply. For the third one here, this one's a little more tricky. I would have the square root of 25 is 5, and then 5 cubed is 125. So your denominator is 0. But now in the numerator, you would have the square root of 25, which is 5, plus 25. Well, 25 plus, 5 plus 25 would be 30. 30 minus 20 would be 10. This would be 10 over 0. That's undefined, not indeterminate. So yet again, since it's not 0 over 0, L'Hopital's rule does not apply. Now, you might have some on yours where L'Hopital's rule does apply, but it would only be because when you try to plug in the limiting value, your numerator and denominator either both go to infinity or both go to 0. That's the only time L'Hopital's rule can apply. Now, all the rest of the problems in this section actually tell us to apply L'Hopital's rule. So we don't have to sit there and think about, should it be applied? We're told to apply it. So when I'm thinking about this first one, obviously it does apply, because if I try to evaluate at 0, sine of 0 is 0 and my denominator is 0. So I can say, okay, let's use L'Hopital. The notation every single time you use L'Hopital, of course, I can't grade your notation on Achieve. They just want the final answer. But on a test, I would. I want to see that h over the equal sign every time you're using L'Hopital. And then you say, well, this is going to equal the limit as x approaches 0. L'Hopital says take the derivative of the numerator. Derivative of the sine of 3x is the cosine of 3x times 3. And then my denominator is just power rule. Derivative of x squared is 2x, and 16x gives me a 16. Now, as soon as I see that, ooh, that denominator is going to be 16, even if I do plug a 0 in for x, I know I'm done. So I can go ahead, plug in the x. I get the 16 in the denominator. Cosine of 0 is 1, so I have 3 times 1 in the numerator for a final answer of 3 over 16. Now, please also keep in mind, this limit notation had to be left in there until I physically was able to plug a 0 in for the place of x and solve out my problem. For my next question, number 5, we have the limit as x approaches 0 of 10x cubed over the sine of x minus x. So of course, this is again 0 over 0. I use L'Hopital. In my numerator, I just use the power rule, and I can say, well, that's going to give me 30x to the second. My denominator, the derivative of the sine of x is the cosine of x. Derivative of x is 1. So now when I'm thinking about this, I can say, well, I still can't evaluate it, because if I tried, my denominator would be the cosine of 0, which is 1. 1 minus 1 is 0. My numerator evaluated at 0 would be 0. So I say, well, no problem. Use L'Hopital again. I always like to say there's no limit to the number of times you can use L'Hopital. Get it? It's a limit problem. There's no limit. Okay, sorry, that wasn't one of my best jokes. But now, I do L'Hopital the second time here. Derivative of 30x squared is 60x. In my denominator, derivative of cosine x is the negative sine of x. And of course, derivative of the constant cancels. So then I can say, well, all right, now can I evaluate it? No, sine of 0 is 0, 60 times 0 is 0. I use L'Hopital again. And I know this will be the last time I have to use L'Hopital, because once I use L'Hopital now, my numerator is just a constant. So I am done no matter what. Well, the derivative of my denominator, derivative of negative sine is negative cosine. Now I evaluate at 0. My numerator is 60. My denominator would be negative 1. And of course, 60 divided by negative 1 gives me the negative 60 over here. That's a little blurry. Let's see if I can clear that up. Yeah, it's a little better. Okay, up next, guys. For number 6, we have the limit as x approaches infinity of this expression, 49x plus 4 over 3 minus 10x. This actually goes back to like pre-calculus, whenever you were finding horizontal asymptotes. You had in rational functions, as long as the degree of the numerator and denominator is the same, we always said the horizontal asymptotes are at y equals the fraction of the leading coefficients. Well, that's going to be the case in this case. Horizontal asymptotes are the same thing as the limit as x approaches infinity. It's just what y value do the x values, does it go to as x goes to infinity? And you can say, well, I know it's negative 49 over 10. How do I know that? Well, I would know that without calculus by just looking and saying, well, the degree of the numerator and denominator is the same. The fraction of the leading coefficients is 49 over negative 10. Final answer. But L'Hopital can also handle it. It just says, okay, since it's infinity over infinity, that's technically indeterminate and a limit. So you can take the derivative of the numerator and derivative of the denominator. When you do that, obviously you get your 49 over negative 10, which doesn't have an x in there for the limit anymore. So you can go ahead and take the limit and it doesn't change. You just get your negative 49 over 10. And that's just my personal preference to always put the negative in the numerator. I think it looks better. Number 7, we have the limit as x approaches infinity of x over e to the x. Well, I already know the answer to this problem before I work it. I knew it was 0. How did I know that? Because exponential functions go to infinity extremely more quickly than just wimpy little polynomial functions. So even if this was x to the billionth power up here, x to the billionth power divided by e to the x as x goes to infinity would be 0. Now, you can see that, and L'Hopital shows you that. It just says, well, okay, yeah, your numerator and denominator are both going to infinity, but what's that ratio going to? Is it going to infinity or is it going to 0 like I mentioned? Well, you can see that real quickly. No matter what power x would be to, as I take the derivative, it's always going to decrease in power. So in this case, it was just an x to the first, so I only had to take the derivative once and I get a 1. Well, my denominator, it's never going to decrease in size. The derivative of any exponential function is that exponential function. So now I can take the limit and I can say, well, the limit as x approaches infinity of 1 over e to the x, that's 1 over infinity, goes to 0. Now, imagine, what if this were an x cubed up there? You would have just had to take L'Hopital's rule 3 times. It would get you down to a constant of 6 over e to the x, which obviously still goes to infinity. No matter what the power on that x is, eventually L'Hopital's rule would show you that the limit is going to 0. But the higher the power, the more annoying it would be because you'd have to use L'Hopital multiple times. Now this next question, same idea. I said any exponential function is larger than any polynomial function. Well, any logarithmic function is smaller than any polynomial function. So as soon as I see a logarithm divided by a polynomial, and whether the limit's going to infinity or negative infinity, I can just say, this is going to 0. The reason I know that is because every single logarithmic function goes off to infinity. Yes, and the y values do go to infinity, but they go there infinitely times slower than any polynomial function. So now in order to show that in this problem, I could say technically, if I just tried to plug the negative infinity in, you get the natural log of an infinite number, which, yeah, that's infinite. You'd have 13 times infinity in the denominator, clearly infinite. So L'Hopital's rule applies because infinity over infinity is one of our indeterminate forms. So I use it. And I can say, all right, derivative of the numerator, derivative of every single solitary logarithmic function in existence. You put what's inside the logarithm in the denominator, and then you multiply by the derivative of that term for the numerator. So it's 1 over f of x times f prime of x. So 1 over x to the fourth plus 4 times the derivative of x to the fourth plus 4 gives me a 4x cubed up there. Now, all of this is the derivative of the numerator. Well, derivative of the denominator is just 13. Now, from this step to this step, please notice I'm not using L'Hopital again. I'm just rewriting. I'm saying if I have a 4x cubed divided by this group and divided by this group, then I have 4x cubed divided by 13 times this binomial. I went ahead and distributed and had 13x to the fourth plus 52 down there. Now, as soon as I see this, a polynomial divided by a polynomial, I know that every single time if I have a limit going off to infinity and the degree of the denominator is greater than the numerator, then that fraction goes off towards 0. And I don't need to worry about whether it's positive or negative. The limiting value is 0, so sign is irrelevant. And that was just since the degree of the denominator is greater than the numerator. Now, if you didn't want to use that logic, you would have had to use L'Hopital's rule 3 more times in order to get down to a constant over a variable to the first power. I didn't want to waste time and show L'Hopital's rule 3 more times in this problem when I already knew from this, and I want you to already know from this, that the answer is 0. In my next question, I have the limit as x approaches 1 of the root of 24 plus x, which obviously that's the square root of 25, which is 5. And then minus 5 times 1 to the 1/5. Well, that's your numerator is 5 minus 5, so 0. Your denominator would be 1 minus 4 plus, that's 0. So I can say it is indeterminate, 0 over 0. L'Hopital should be able to handle it, so I use L'Hopital. Derivative of the numerator. I thought of this as the group to the 1/2 power. So I said its derivative is going to be 1/2 times that group to the negative 1/2. And then I thought about times the derivative of the inside, but that's just 1. So all of this is the derivative of the first. Then I move to the second term. 1/5 times 5 just gives me a 1. So you can see I just have minus 1 times x to the 1/5 minus 1 power gives me x to the negative 4/5. My denominator, just power rule, would be 2x minus 4 down there. As soon as I see that that denominator is 2x minus 4, I know I'm done because I can plug a 1 into that denominator and it will no longer be a 0. So it's not going to be indeterminate. I go ahead and evaluate it. 2 times 1 is 2. My denominator is going to be 2 minus 4. My numerator, when I plug a 1 into this, I can say, well, this group is really in the denominator inside of a square root. I'm going to have 1 over 2 on the square root of 24 plus x, which gives me 1 over 2 on the square root of 25, which is 1 over 2 times 5. That second term, when you plug a 1 in, doesn't matter what power 1 is raised to, it's still a 1. So you have 1/10 minus 1. I thought of that as 1 over 10 minus 10 over 10 to get my negative 9 over 10. That's divided by negative 2. So our final answer is positive 9 over 20. For number 10 here, again, we have a limit going to infinity. This one's very similar to number 6. It might even be an easier version of number 6, or, well, about equal level of difficulty version. As soon as you see your limit going to infinity, you can say, hey, degree of the numerator and denominator is the same. Your answer is going to be the fractional leading coefficients and 16 over negative 7. Done. If you wanted to use L'Hopital's rule on it, you'd say, well, all I need to do is take the derivative of the numerator and the derivative of the denominator and see that, well, there's no x left to plug in. So clearly, my answer is negative 16 over 7. Next page here. For the 11th problem here, they gave me a limit as x approaches negative infinity of a quadratic over a quadratic. So again, I was thinking that the negative infinity is going to be irrelevant because my leading power, it's x squared. So infinity's negative, and a negative number squared is positive anyway. So I could just say, well, this is the same thing as the limit as x approaches positive infinity. And anytime I have a rational function with the same degree in the numerator and denominator, my answer is going to be the fraction of the leading coefficient. So before I worked this problem, I knew the answer was -9/2. And I would like you to know that too. But I went ahead and showed work with L'Hopital. So L'Hopital says it is indeterminate since as you plug in an infinity, your numerator and denominator are both going to infinity. Then you should be able to take the derivative of the numerator and get 18x plus 5 over the derivative of the denominator and get your -4x. But at this point, you'd still see, well, if I try to plug in x, it's still going to give me infinity over infinity. So take L'Hopital again. That simplifies your problem down to 18 in the numerator and -4 in the denominator. Well, the limit as x approaches negative infinity of 18 over -4, that's just going to reduce down to -9/2. Same thing as if we just looked at the beginning of the problem. Now, number 12 is one of those, again, you could just look at the beginning of the problem and say, hey, the answer is 5/4. Sadly, that would work. But the reason that that works is because if you try to plug in a 0, you'd say, well, it's the sine of 0 over the sine of 0. That's 0 divided by 0. That's indeterminate. So we use L'Hopital to determine it. And so you say, okay, then this is the limit as x approaches 0, derivative of the numerator. Derivative of the sine of 5x is cosine of 5x times 5. Derivative of the sine of 4x is the cosine of 4x times 4. And then I can say, well, all right, can I plug in the 0 now? Certainly, because the cosine evaluated at 0 is 1. So your numerator is just 5 times 1, your denominator is 4 times 1, you get your 5/4. For the next one, if I have the limit as x approaches 0 of the tangent of 14x divided by 8x, I know that the tangent evaluated at 0 is 0. 8 times 0 is obviously 0. L'Hopital does apply. So I take the derivative of the numerator. Derivative of the tangent is secant squared of the angle times the derivative of the angle. So I get 14 secant squared 14x. Derivative of 8x is just 8. As soon as I get that 8 down there, I know that I can evaluate because it's no longer 0. So I can say, all right, my denominator is 8. What's my numerator? Well, it's the secant squared of 0. And you say, well, I don't know what the secant squared of 0 is. Sure you do. It's the reciprocal of the cosine squared of 0. Cosine of 0 is 1. Therefore, the secant of 0 is 1. Secant squared of 0, still 1, because 1 squared is still 1. So your numerator is just simply 14 times 1 over your 8. And of course, that reduces down to 7/4. Now, again, could have you just looked at the beginning of the problem and said, ooh, John, the answer is going to be 14/8, which reduces down to 7/4. Sadly, yes. That kind of takes the fun of that problem away. What about number 14? You'll see it took me quite a bit more work to show it. That's because it had a lot of chain rule in my problem. So taking a look at it with me, we have the limit as x approaches 0 of the sine of 15x minus 15x cosine of 15x all over 15x minus the sine of 15x. So first of all, I thought about, well, could I just plug the 0 in? No, because your numerator sine of 0 is 0. 15 times 0 makes that entire second product 0. Your denominator, you'd have 15 times 0 minus the sine of 0, still 0. So I use L'Hopital. And when I use L'Hopital, I have to remember I'll take the derivative of this term using the chain rule, derivative of this term using the product rule and chain rule. So the first term, derivative of sine, is cosine of the angle times the derivative of the angle. I get 15 cosine of 15x. Then I'm subtracting this entire product. So I can say, well, all right, then you're subtracting. The first term of the product rule tells me to take the derivative of the first. So I have minus 15 times the second. So I have minus 15 cosine of 15x. Now, it would also be minus the second term in the product rule. Well, why is it a plus sign here? Please think about that. I would be saying minus 15x times the derivative of cosine. Well, derivative of cosine is negative sign. That's why that had to become plus, because I was subtracting the entire product rule, but the last term was negative, thus that became a plus there. So I have plus the first times the derivative of the second, and when I take the derivative of cosine and I get that negative sign of 15x times 15, I multiplied that 15 by the existing 15 out in front, and I got my 225x sine of 15x. So then my denominator, much easier to take the derivative down there. Derivative of 15x is just 15. Derivative of the sine of 15x, of course, gives me my cosine of 15x times 15. It was subtracted here, still subtracted here. Now, when I think about this, if I try to plug in a 0, my denominator would be 15 minus 15. My numerator would be 15. Well, obviously, these first two terms cancel each other out. 15 cosine 15x minus 15 cosine 15x. So the only term in the numerator is really this product. And I know it's 0 because it has x as a factor that would make the entire product 0. So then I come down here and I can say, all right, when I use L'Hopital again, and I had to scrunch in my limit as x approaches 0, I almost forgot it. Well, I did forget it and had to go back and scrunch it in. These two terms cancel, so my entire numerator is just the product rule derivative of this term. So I said, okay, derivative of the first, 225 times the second, sine of 15x. That's where that came from. Then I said plus the first, 225x, times the derivative of the second, which would have been cosine 15x times 15. Well, then I had to say, well, that 15 can just multiply the 225 out front and give me 3,375x cosine of 15x. And at this point in the problem, I started to think, gosh, I might be doing something wrong to get a coefficient that big. But no, it's correct. Now, my denominator, when I took the derivative of this, derivative of the first term, 0. Derivative of the second term, it's a negative cosine. Derivative of negative cosine is going to be positive sine. You'd get 15 sine of 15x times 15. That's where the 225 came from, 15 times 15. So now I'm looking at this and saying, can I evaluate this at 0? Nope, because the sine of 0 is 0. Your numerator, this term has a factor of x, which makes it 0. And then this is a sine of 0, which makes that term 0. So everything's still 0 over 0. I use L'Hopital again, thinking surely this will be it. So the first term, 225 sine of 15x. I can say, well, derivative of sine is cosine. So this is going to be 225 cosine of 15x times 15. 225 times 15, again, gave me my 3375 cosine of 15x. Now I move to this term, and I remember it's a product. So I say derivative of the first is going to give me my 3375 times the second cosine of 15x. And then the next term is plus the first 3375x times the derivative of the second, and derivative of cosine is negative sine. So I'd say, well, that's why that sign out in front became negative. It would have been plus a factor of negative sine. It's better just to say minus. Where did that 50,625 come from? Because I had to yet again multiply by the chain rule derivative of the angle. So 3375 times 15 gave me my 50,625. And then mercifully, I was able to take the derivative of the denominator and evaluate at 0, because now I can say, well, these terms that have a cosine in the numerator, they don't have a factor of x. So that's just going to be 3375 times 1 plus 3375 times 1. I know that the sine is 0, and this factor, of course, is 0. So that third term is just nothing. It's a 0. My denominator is going to give me 3375 times 1. So I can say, well, all right, then your problem is going to become 3375 plus 3375 over your denominator of 3375, which clearly simplifies to be a nice answer of 2. It's kind of surprising to get that beautiful of an answer after some of the coefficients in that problem, but that's a cool problem. Number 15. So in 15, we have our first problem in which I believe we have to force a fraction. All the other ones up to this point have already been in fractional form, which that's nice for L'Hopital because L'Hopital only applies to fractions in the general sense. We can make other expressions into fractions and use L'Hopital. So when I'm looking at this case and saying, well, I have the limit as x approaches 3 pi over 2. Clearly that first term here, if x is approaching 3 pi over 2, this term is approaching 0. The tangent of 3 pi over 2 divided by 3, that'd be the tangent of pi over 2. The tangent at pi over 2, it's approaching infinity because your sine is approaching 1, your cosine is approaching 0. So we have a number approaching 0 times a number approaching infinity. And you say, well, all right, let's see what we do. In order to try to simplify this, I had to put it as a fraction. So I thought it was easier to move the trigonometric function to the denominator because I know the reciprocal of tangent is cotangent. So a factor of tangent in the numerator is equivalent to a factor of cotangent in the denominator. Now that I have it in this form, I should be able to use L'Hopital. Derivative of the numerator was simple enough. It's just a linear function with a coefficient of 1. My denominator, I have to remember, derivative of cotangent is negative cosecant squared of that angle times the derivative of the angle. So I can say, well, it's negative cosecant squared of x over 3. And if you think of that x over 3 angle as 1/3 x, you can easily see, oh, the derivative of the angle is 1/3. Now, in order to simplify this, I was just thinking, well, all right, how could I rewrite this? I know that I have a factor of negative 1/3 in the denominator. I could multiply by negative 3 over negative 3 and say, well, factor of negative 1/3 in the denominator is the same thing as a factor of negative 3 in the numerator. A factor of cosecant squared in the denominator is the same thing as a factor of sine squared in the numerator. So I just rewrote it to make it more friendly to work with and say, same thing as negative 3 sine squared of x over 3. Now can I evaluate? Of course, because you say, well, if you plug in your 3 pi over 2, that's going to be divided by 3. And so this just becomes sine squared of pi over 2. Now, please remember how to evaluate this. You just think, well, all that is, I need to figure out what the sine of pi over 2 is. And that's easy. It's straight up on your unit circle. It's 1. So the sine of pi over 2 is 1, and then square that answer. 1 squared is still 1. We multiply that by the coefficient of negative 3, and we get our answer of negative 3 is what it be. For number 16, you have the limit as x approaches pi over 2 of the cosine of 15x over the sine of 4x. And this is one of those annoying problems similar to number 12 where you can say, ooh, the answer is 5 over 4, John, yay. Yes, sadly it was. Same thing here. The answer is 15 over 4, John. Yes, sadly it's going to be. But let's talk about why rather than just use that cheapskate trick. So when I'm thinking about this, I have the limit as x approaches pi over 2. So that cosine of 15 pi over 2, I'm thinking, well, the cosine of any odd number times pi over 2, that's going to be 0. Whether it's up on our unit circle or down on our unit circle, the cosine of an odd multiple of pi over 2 is going to be 0. Sine of 4 pi over, that's the sine of 2 pi, that's 0 because that's at the that's at the origin, 0 or 2 pi. The sine there, the y-val component there is 0. So I can say, okay, L'Hopital should apply. I apply it. Derivative of cosine is negative sine of the angle times the derivative of the angle. So I get negative 15 sine of 15x. My denominator now, derivative of sine is cosine of that angle times the derivative of the angle. So I get 4 cosine of 4x. Now when I'm thinking about this, I can say, well, I know I'm done at this point because I can plug in the pi over 2. When I plug in the pi over 2, I would get the cosine of 4 pi over 2. That's the same thing as the cosine of 2 pi. In my numerator, the sine of 15 pi over 2, and I'm thinking, okay, 15 pi over 2, that's going to be 3 revolutions beyond, and it's a coterminal angle to 3 pi over 2. It's 3 pi over 2 plus 12 pi over 2. So I can just say, well, that's coterminal to straight down on the unit circle. The sine at that value is -1. So my numerator becomes -15 times -1. My denominator is this 4 times the cosine evaluated at 2 pi or coterminal to 0. I get a 1 there. And I can say, well, then my answer is just going to be +15 over 4. And sadly, if you took the shortcut way out, you got the same answer, which is depressing. I'll make sure. So good news, good news. I will make sure to never put an answer, or sorry, a problem on a test where the obvious answer in the beginning ends up being the answer. That's number 17. We have the limit as x approaches pi over 2, and I have a secant x minus tangent x. So you can say, okay, L'Hopital only applies to fractions, so I need to try to make a fraction in this problem. Well, we can do that. So the first thing I'll do is I'll say, well, the secant's the same thing as 1 over cosine. Tangent's the same thing as sine over cosine. As soon as I do this, I can say, well, they already have a common denominator, so I can go ahead and combine my numerators and say this is 1 minus sine x over cosine x. Now, can I evaluate that at pi over 2? Not yet, because your numerator would be 1 minus 1. Your denominator, cosine pi over 2, would be 0. So it's 0 over 0. Well, that's okay, because L'Hopital can help. I use L'Hopital. So when I use L'Hopital, the derivative of negative sine x is going to give me a negative cosine x. The derivative of cosine x is going to give me a negative sine x. So I have negative cosine divided by negative sine. And I can say, now can I evaluate that at pi over 2? Well, your numerator is going to be a 0 because cosine pi over 2 is 0. But your denominator, remember the sine of pi over 2 is 1. So your denominator is a -1. And as long as your fraction is not 0 over 0 or infinity over infinity inside that limit, it's no longer indeterminate. And we have our final answer. So you just say, well, your final answer is 0 divided by -1, which is simply 0. Now, for 18, we have the limit as x approaches 8 of e to the x squared minus e to the 64 over x minus 8. So when I try to plug in an 8 into this, I'd say, well, your numerator would be e to the 64 minus e to the 64. Your denominator would be 8 minus 8. So I use L'Hopital to evaluate. When I use L'Hopital, I have to remember the derivative of every single exponential function in existence is that exponential function times the derivative of its exponent. And it's also extremely important that you remember the second term in the numerator. Yes, it's an exponential term, but it's not an exponential function. That's just some irrational constant. It's an enormous irrational constant, but the derivative of any constant is 0. So I can just say, well, second term cancels out when I take the derivative. My denominator clearly has a derivative of just 1. So now I can evaluate this at 8. And when I do, this would be e to the 8 squared, which is e to the 64. And then times 2 times 8. So I get times 16 all over 1. Better written as 16 e to the 64th power. For 19, we had x limit as x approaches 0 of 8e to the 5x minus 8 divided by the sine of x. So when I'm thinking of this problem, I can say, all right, can I go ahead and plug in a 0? Not in the denominator, and actually not in the numerator either, because an exponential function to the 0 power is 1. So you have 8 times 1 minus 8. You've got 0 over 0 right now. I use L'Hopital to see if that helps, and it should. Derivative of 8e to the 5x would be 8e to the 5x times 5. That's where the 40e to the 5x came from. My denominator derivative of sine is cosine. Now I know I'm done because the cosine evaluated at 0 is just 1. Your numerator evaluated at 0. Please remember what I said. Any exponential function to the 0 power is 1. So you have 40 times 1 up there. Well, 40 times 1 over 1 gives me my final answer of 40. Now, the next one, and I think it may be the only one in this entire assignment that ends up being where the limit does not exist. It's undefined. I have a problem. The limit as x approaches 0 of e to the 2x minus 1 minus 13x. And mine had the group 13x squared in the denominator. There's no reason for you to not go ahead and think of that algebraically. And so I thought of, well, 13x quantity squared, that's the same thing as 13 squared times x squared, 169x squared. Easier to take the derivative if you do that. So I thought of this as my denominator. Now, no matter how you think about it, if you try to plug in a 0 in the beginning, you're going to get a 0. Your numerator is 1 minus 0. Your denominator is 169 times 0 squared. L'Hopital is going to give us a derivative in the numerator of e to the 2x times 2. So I have 2e to the 2x. Second term's just a constant, so its derivative is 0. Derivative of negative 13x is minus 13. So now I have my numerator derivative taken correctly. My denominator, I would just say, well, 2 times 169 gives me 338 x to the first. Now when I think, can I plug in the x? If you look at the denominator, you might think you can't because it's still a 0, but you actually can and should because your numerator is no longer 0. If you try to plug an x into your, a 0 in for x in your numerator, you're going to get 2 times e to the 0. That's 2 times 1 is 2 minus 13. Your numerator is negative 11. Your denominator is 0. If you try to keep on using L'Hopital's rule, you're going to get the wrong answer. The answer to this question, as soon as you get here, you say, that's not indeterminate form. That is undefined form. This limit does not exist. Now, for 21, we go back to a problem where it's not put in terms of a fraction for us. That's no big deal. I can just say, well, all right, I have the limit as t approaches 0 from the right of 4 sine of 9t times the natural log of 9t. And the reason that t has to approach 0 from the right is because the natural log would not exist for numbers approaching 0 from the left. They have to approach 0 from the right. So the first thing I did is I just said, well, that 4, that's just a factor of 4. I can bring that out in front, and you'll see in the next step, I just brought it out in front of the entire limit. That factor of 4 doesn't have to be part of your problem. It can be an outer factor multiplying the entire limit. Now, once I bring out that 4, what am I left with? I'm left with this product. And just like I did last time where I had, I think it was 16 on the previous page, where I had a trigonometric term and another term, I said it's easier to make the trigonometric term go to the denominator. Same thing here. I'm going to leave the natural log in the numerator. I'm going to move that sine to the denominator. The reciprocal of sine is cosecant. So I can say this is equivalent to the original expression. But the reason it's superior is that now I can use L'Hopital. So I'll use L'Hopital, and I'll go ahead and show the 4 can be brought out in front of the limit. And then it's 4 times the limit as t approaches 0 from the right of the derivative of the numerator. Well, your numerator's derivative would be 1 over 9t times the derivative of 9t, which is 9. So it'd be 9 over 9t, simplifies down to be 1 over t. Your denominator, derivative of cosecant is negative cosecant cotangent. So I get negative cosecant 9t cotangent 9t times the derivative of the angle 9. That's where that negative 9 came from there. So now I can say, well, is this better? Oh, I need to simplify. So you'll notice from this step to the next, I am not using L'Hopital. I'm just trying to make sense out of what I have. I know that this term is 1 over sine, so it's like a factor of sine in your numerator. This term is cosine over sine, so it's like another factor of sine in your numerator and a factor of cosine in your denominator. So notice what I did here. I said, I'm going to take this negative 9 bring it on. It's just a constant factor. It doesn't care what t is approaching. I'm going to bring that -9 and factor it out and say, well, my out front, I'll have -4/9 times the limit as t approaches 0. And then let's rearrange these terms. That t belongs in the denominator. I put it down there. Both of these terms are divided by the sine of 9t. So that sine squared 9t goes up in the numerator. And then you say, yeah, but you had this one is cosine 9t over sine 9t. You got rid of the sine 9t by putting it in the numerator. You still have a cosine 9t in the denominator. So this is the trigonometric simplification of this. Then I can say, well, can I take the limit? The sine of 0 is 0. You have a factor of 0 in the denominator. So still the answer is no, I cannot. It's still 0/0, still indeterminate. So L'Hopital should be able to help. I still have my -4/9 out in front of my limit. And then on the inside, I'm taking the derivative. You need to think of this as the sine of 9t quantity squared. So when you take the derivative, the 2 comes down in front. Then you'll have times the sine of 9t to the first power. Then you say times the derivative of what was inside. Well, derivative of sine is cosine of that angle 9t times the derivative of the angle 9. And then I can say, well, all right, what about the denominator? Product rule down there. Derivative of the first is 1 times the second plus the first t times the derivative of the second, which is going to give me my negative sine of 9t times a -9. At this point, I'm thinking, can I take the limit as t approaches 0 now? And I can say, well, my numerator is going to be 2 times 9 times sine of 0 is 0. So that's going to make all of that 2 times 9 times 1 times, makes it all 0. What about your denominator, though? Oh, you're done, because this term right here, cosine of 9t, as t approaches 0, that's the cosine of 0, which is 1. You're going to have 1 plus 0, because t is going to 0. 0 times any number is 0. So I'm going to have 1 plus 0 in my denominator. This limit goes to -4/9 times 0/1, which that's just -4/9 times 0. My answer is 0. It's a lot of work to get an answer of 0. Now we go from a problem that took quite a bit of work to one of the shortest problems in the assignment. 22, it's pretty easy. We just have to remember derivative of any exponential function is that exponential function times the derivative of its exponent times the natural log of its base. So when I give you this function and you say, well, can I take the limit to begin with? No. 7 to the 0 is 1. 3 to the 0 is 1. So your numerator is 1 minus 1, 0. Your denominator is 0. L'Hopital says, well, that's indeterminate. You should be able to take the derivative of the numerator and denominator and then try to evaluate again. So I do that. Derivative of any exponential function is that exponential function times the derivative of its exponent, which is 1, times the natural log of its base. Same thing here. Derivative of 3 to the x is 3 to the x, natural log of 3. Clearly, the derivative of x is just 1, so our denominator is a 1. As soon as I see that 1 down there, I know I'm done, though, because L'Hopital only applies if it's 0/0 or infinity over infinity. It's no longer either of those. So I can say I need to take my limit. When I do, any exponential function to the 0 power is 1. So you're going to have 1 times the natural log of 7 minus 1 times the natural log of 3. That's just natural log of 7 minus natural log of 3 and achieve once the exact answer. So you could leave it like that. Or if you wanted to condense and call that the natural log of 7/3, that would be cool. For 23, it gave you a problem in which logarithmic differentiation becomes necessary. And you need to see that because the function that they gave me in this problem, I can say, well, it's certainly not a fraction for one. And more important than that, I certainly can't take the derivative of x to the 4/x. It doesn't satisfy any of our derivative rules. It's not an exponential function. It's not a polynomial function. So instead, what I do in this case is I just said, well, let's let y equal what we're trying to take the limit of. And then let's think about that. Let's simplify it with logarithms. This is the logarithmic differentiation part. Instead of directly attacking y, we're going to attack the limit of the natural log of y. So I say, let's take the natural log of y and then the natural log of the right-hand side. The natural log of the right-hand side, when you do that, you can say, well, then if I take the natural log of the right-hand side, then any exponent can come down in front. That's precisely what I did. The exponent 4 over x comes down in front times the natural log of x. That's just using logarithmic properties. And then I can say, well, all right, I know L'Hopital is going to apply if I can create a fraction. This makes it creating a fraction really nice because I can say 4 over x times the natural log of x. It's the same thing as 4 natural log of x over x. Now I come down here and say, all right, I need to find out what the limit as x approaches infinity of y is, but I can't do that directly. So I'll find the limit as x approaches infinity of the natural log of y, which is going to equal the limit as x approaches infinity of this fraction. Right now, if you tried to plug in infinity, natural log of infinity is infinity. Your denominator is also infinity. So you'd say, well, it's indeterminate. I use L'Hopital. Take the derivative of the numerator and you'll get 4 over x. Derivative of the denominator is just 1. So then you can say, can you take the limit as x approaches infinity of that expression? Well, sure. 4 divided by infinity goes to 0. Now, that's the limit as x approaches infinity of the natural log of y is 0. In order to get to our answer, you'd need to get rid of that natural log. You would do that by exponentiating each side. When you exponentiate the left-hand side, that natural log goes away and you have the limit as x approaches infinity of y. You exponentiate the right-hand side and it becomes e to the 0 power. You say, well, any exponential function to the 0 power, 1. Final answer, 1. For 24 here, we have our first and only, sadly, inverse trig limit in this section. We have the limit as x approaches 0 of 3 inverse sine of 8x over 4x. So here you have to remember your inverse sine derivative formula. It's 1 over the square root of 1 minus the argument squared times the derivative of what's inside that argument. That's what I did here. So that 3 is going to go along with the derivative. I just went ahead and put it in the numerator over the square root of 1 minus what's inside of it, 8x quantity squared, times the derivative of what's inside of it, 8. That's the chain rule derivative for the inverse sine, over the derivative of the denominator, which is just a 4. And then what I did is I just said, well, 8 divided by 4 is 2. 2 times 3 is going to give me a 6. I'm going to get 6 over 1 minus 8x quantity squared. 8x quantity squared is 64x squared. Now, can I evaluate this when x goes to 0? Well, sure. If you do, that 64x squared term just goes to 0, and you'll have 6 divided by the square root of 1. 6 divided by the square root of 1 is 6. This will conclude your L'Hopital homework section. This is one of the topics that you really need to get comfortable with. L'Hopital is never going away through any of your calculus classes. It's continually used to find limits of functions throughout Calc 2, Calc 3 differential equations. So please make sure you are good with this concept and let me know if you have any questions.